Okay, I had a question about determining empirical formulas from percentage compositions. That's chapter 7. And so what you can do is, since you have the answers here, you can look at a whole variety of the examples. So we just break down what they did here. It was 52.2% carbon. And so here the first step is we assume a 100 gram sample. We have 100 grams and 52.2 out of 100 will be carbon. So this is 52.2 grams of carbon. 13.0% hydrogen, which translates to 13.0 grams of hydrogen. Oxygen is at 34.8%, 34.8 grams. And then we do gram to mole conversion. This is more than a mole. A mole of carbon weighs 12.01 grams on average. This actually turns out to be 4.35 moles. A mole of hydrogen weighs about 101. So we got 13 grams, it's about 13 moles. And a mole of oxygen weighs 16, so this is a little over 2 moles of oxygen. And the formula is the mole ratio. Except, this is not a simple mole ratio. And so what we do is we try to break it down by dividing it by the smallest number of moles. Like here, 2.18. And so we'll divide these three by 2.18. And so 2.18 divided by 2.18 gives us 1.00. 12.9 divided by 2.18 gives us 5.92. And 4.35 divided by 2.18 gives us 2.00. And so here you can see the mole ratio. The simplest mole ratio is the formula. So it's a 1 to 6 to 2 ratio if we round 5.92 to 6, which they did here. So 1, 6, 2 ratio. So 2 carbons, C2, 6 hydrogens, H6, 1 oxygen.
How would you go on to the molecular formula?
We need additional piece of data to get the molecular formula. We can't here. There's no way we can get the molecular formula.
Yeah, could we do the one on the practice test?
Yeah, we could do that one. To get the molecular formula, you need to know how much a molecule weighs. What we know is how much this weighs. 2 carbons would be 4, 6 hydrogens about 6, so this is 30, plus 16. This is about 46 U per molecule. And so if we weigh an individual molecule and it comes out to 46 U, then this is it. But let's say we weigh out an individual, this is an empirical formula. If it comes out as a multiple of 46, say 92, then you double, 3, triple, etc. So we need to know what the molecular mass is. How do you determine the molecular mass of an unknown molecule? What instrument can you use to determine how much a molecule weighs? Mass spectrometry. There are different techniques. One of the techniques for learning this type of stuff is seeing as many examples as possible. So another example here. We do the same thing. Percentage. I'd say assume 100%, so this would be 15.9 grams of boron, 84.06 grams of fluorine, then convert it to moles, and then divide it by the smallest to get the mole ratio. Sometimes we have to do an additional step. Somebody asked me this morning, does it have to be 100 grams? No. Excuse me, sorry. This one is different. This one is a little bit trickier, but here we don't really have to. It's 11.89 grams of iron to produce 16.99 grams of pure oxide. And so out of the 16.99 grams, 11.89 grams will be iron, the rest will be oxygen. And so we don't have to do a 100 gram sample here. We could just take the grams of iron and the grams of oxygen and convert it to moles. That's what they did here. And so we look at variations here. Here in this particular example, they didn't assume. They just calculated. And so the grams of oxygen would be 1699 minus 1189, which comes out to 5.10 grams. And so we don't have to do 100%, we'll just do 1189 grams of iron, 5.10 grams of oxygen. This is the mass ratio. We don't want the mass ratio, we want the mole ratio. So we do a gram to mole conversion and get the simplest mole ratio. This simplest mole ratio comes out to 1 to 1.5. 1.5 is not good. I mean, we could round it up to 2 or round it down to 1, but it's gonna lead to large round-off error. So rather than doing that, we'll just double everything. If we double everything, then we'll get a 2 to 3 ratio, which is better than having this huge round-off. Does it make sense? And so we see variation. So this is Fe2O3 here. What I do, and this is a trick I learned when I was a student at UCLA, is this is something I never did until I saw somebody else do it. I never looked at every single homework problem in the chapter. Just wouldn't do it. I'd just do the bare minimum. But you know, the person who was getting the top score in the class looked at every single homework problem. And I was sitting next to the person who was getting top score. In fact, I became friends with the person who was sitting next to me, his top score, and I asked him, you know, what he did to get the top score in the class. You know. And these are the things. So I started doing it too. So I look at every single problem. I don't look at just what's assigned. You know, that's the bare minimum was what's assigned. If you want to be one of the top students in the class, you got to do a little bit more than, you know, the bare minimum. And so that's what I'm going to be. I want to be scoring top score, or at least up there, not at the bottom, which I was when I transferred there. I was not. So anyway, I got here, this one looks the same, like 39.12. This, we're going back to grams, so I call it 39.12 grams of carbon, 8.772 grams of hydrogen, and 52.11 grams of oxygen. Convert that to moles, take the mole ratio. Here, this one, the same thing, you know, percentage to grams and grams to moles. So this one, the answer's there, like half of these are going to have the answer there. So we have the mass ratio, we convert the mass ratio into mole ratio, then we divide by the smallest. We divide by the smallest, we can see it comes out to 1:1:3 ratio. So this would be the empirical formula. This is CHF3. It turns out this is also the molecular formula for this, CHF3. How do I know? Because I know this molecule here. But you would need additional information. You'd need to know how much the molecule weighs. 62, same. You know, one thing I do, I look at is I look for variations in the way the question's asked. You know, how many different ways do they ask the same question? Now I notice something different. When I come here, an antifreeze coolant, okay, this is the same, 38.7% carbon, so it means 38.7 grams of carbon, 9.7% hydrogen, which means 9.7 grams. So I have the mass ratio. 38.7, 9.7, 51.6 mass ratio. I need the mole ratio. So I convert that to moles, figure out the empirical formula. But what's different about this problem? It has the molar amount. They're telling us what a mole of molecules weighs. So this is a mole of molecules weighs 62.0 grams, which means an individual molecule should weigh about, this is a mole of molecules, so an individual molecule weighs about, how many U? .0 U. Remember, the molar mass and molecular mass are going to be numerically the same. So let's see the difference they did here. Everything looks the same except they did one extra step. So we have the mass ratio, and we convert each of these into moles. This one divided by 1201, this one divided by 1008, this one divided by 1600. We get these. Okay, then we divide by the smallest number, 322, so that converts these to 1. This one's 3, so it's 131. That's the empirical formula. Now this unit, the empirical unit weighs, okay, carbon's 12, hydrogen's 1, so it's about 15, 16, this is about 31 U. So an individual molecule of this weighs about 31 U. If I had a mole of these molecules, it would weigh 31 grams. And so 31 grams, was that right? No, that's not right, because what they told us is that a molecule of this weighs 62 U, and a mole of molecules weighs 62 grams. And so do you see the mass of the empirical unit does not match the mass of the molecular unit, and therefore they aren't the same thing. The empirical formula and the molecular formula are not the same thing. And so what we have to do is, we get this factor. It turns out the molecular unit weighs twice as much as the empirical unit, therefore the molecular formula should be twice that of the empirical formula. And so in other words, it's not CH3O, it's C2H6O2. This is the formula for this. And this unit weighs 62 U as observed in experiment. They weighed an individual molecule of this on the mass spectrometer, or use some other techniques. There are other techniques to get it. The mass spectrometer would be easy. I'll look at 64. 64 is a mirror, same type of problem. Percent by masses converted to moles. So we've got the mass ratio, mole ratio, empirical formula. And then they give us this. This is what we need to determine the molecular formula. We can skip those, since those problems don't have the answers. Go here and find out. It's the same problem, except this problem has a twist. What's different about this problem? So here we have 73.1 grams of chlorine, 24.8 grams of carbon, and the balance is hydrogen. What do they mean by the balance is hydrogen? What they mean by this is a compound of chlorine, carbon, and hydrogen. The chlorine, carbon, and hydrogen have to add up to 100%. This compound's only made up of 3 things. And so if we know how much chlorine and carbon we have, we can figure out how much hydrogen we have by figuring out the difference. It's got to add up to 100%, so it's going to be 100% minus that, those 2. And so this has an extra twist to it. We could easily see it has an extra twist because we're already conditioned. We already saw all those other problems. We're conditioned to saying this. And so we got to figure out how much hydrogen there is. Well, it all has to add up to 100. So if I take 73.1 plus 24.8, it comes out to 97.9. So 97.9 is not 100%, so in order to make it 100%, there must be 2.1 grams of hydrogen. So that's the first thing we have to do. And then we got the mass ratio, converted to mole ratio, get the simplest mole ratio. Simplest mole ratio, we can round these all to 2. And so it comes out to this. This is ClCH. But a ClCH, how much does that weigh? Cl's 35, carbon's 12, so it's about 47, 48. This is just approximately 48. How much does a molecule of this weigh? A molecule of this weighs 97. And so I'm halfway there. And so it must be Cl2, C2H2 as the molecular formula. This one, a compound is found to contain sulfur and chlorine. And so this doesn't have that extra twist here, and then it has this math. And so this is very similar to the ones we saw earlier. There's no real difference to this. That's it. So we've done every single, or looked at every single problem. Okay.
Can you go over problem number 75 from chapter 9?
Chapter 9, 75.
Chapter 9.
What number was it?
She's coming. Oh, sorry, chapter 75, or, I mean, sorry, number 75.
Number 75. Number 75, that's in there, John. This one? When solid lithium is added to water, hydrogen is released. I'm not gonna be.
I would just say lithium is added to water, what happens? What is the formula for lithium? And water?
This almost looks like what type of reaction?
Yeah, it almost looks like single replacement. It would be single replacement if we call H, HOH, you know, so this is an A plus BX type reaction. Do you see that? A plus BX. And so a lot of times you can treat water as your BX like this, an HOH. The two ways we could do it, we could do it single replacement or we could do a chart method. If we did a single replacement, what does this form? LiOH plus hydrogen gas. All right, what is lithium? Solid, liquid, gas? Water is a liquid. LiOH? Group 1 salts are all aqueous, so it's aqueous. We'll just leave it blank. And then we look for the activity series. The activity series is on that chart up there. Or on our chart. Let's take a look at our chart. So we're comparing Li with what? H2. And so this one should be easy. The Li versus H2, which one's more active? Li. In fact, you already have memorized which one of these is most active? Lithium. It's actually just balanced. Or is it? No, it's not balanced. I gotta balance this. How do I balance it? Yeah, that's right. That'll give me 2 hydroxides here, 2 lithiums, 2 hydroxides. And the 2 hydrogens for H2. That's one way of doing it. This is not the way, and this is the way they do it in Chem 4. Probably would have done it a different way. I probably would have used the chart method. But, you know, this is fine as well. Actually, there's a reaction here. Let's take a look at the answer. 2 Li solids plus 2 H2O liquids yields, oh, they wanted an anionic. I didn't finish this then. This is the CE, and then we'll get the IE. What do we do with lithium in the IE? It stays the same. Water? Stays the same. lithium hydroxide breaks apart into 2 Li plus 2 OH minus. H2 stays the same. And so this is the IE, and there are no spectators, so it's the IE and the NIE both. And so, uh-huh.
Why does H2O stay the same?
Why does H2O stay the same? Because what we're doing in the IEs, we're looking at what water can do. Can water pull apart water? And so we're looking at water. And so other waters are going to come to this and try to pull it apart. It so happens that a water can come and break it apart, but it's highly unfavorable because it's going to form hydronium and hydroxide. This is called autoionization. And so water, we're looking at autoionizing into H plus and hydroxide. It's autoionization because who's breaking apart water? Breaking it apart. And so it's autoionizing. Out of 1 billion water molecules, only about 4 will break apart. So 4 out of 1 billion. That 4 out of 1 billion is very important for pH. But for chemistry, we're doing just the major species. The ionic equation is the major species. And so when you have a glass of water, does that glass of water consist of H plus and OH minus? You know, are you drinking strong acid and drain cleaner with each glass of water? No, it's because the water molecules stay together as H2O. So very few actually break apart. Okay, other questions?
When you do a chart method, it's always when you have an aqueous compound when you add H2O. Or is that only when you have acids?
Both. When you have acids, there's water around, like acetic acid, hydrochloric acid. There's water around because acid are typically water mixtures. The acid. We do both, unless it's solids. Unless you're given solids, like this is Is there any water around this one? No, but this one you might be able to guess what would happen here. What would you guess might happen? What type of reaction does it look like? Single replacement. But we could also do it the chart method. You know, as far as reducers go, we have aluminum solid versus, you know, oxide. Which one loses electrons easier, oxide or aluminum? Is oxygen happy at -2? Actually, you know, you got to see a lot of patterns before this stuff. You know, there's a certain minimum amount of knowledge, basic knowledge you need to discuss this. Otherwise, there's that saying, you know, have you ever heard that saying, a little bit of knowledge can be a dangerous thing? A little bit of knowledge can be a dangerous thing. Because you haven't seen enough, you know, to realize it might be dangerous. Oh, let me ask you this. There's no water around here. This is going to go to, oh, actually there is. Water's a product in this. Something like this. Oh, this is what type of reaction? Is this metathesis, acid base, or redox? Here's a redox. What's the oxidizing agent? Oxidizing. That means this is a reducing agent. It makes sense. This is a reducing agent because it's electron rich. Carbon, what's the charge on carbon? -4. You know what this makes this? This makes it, this is carbon is +4. This makes this the oxidizer. This must be the reducer. And so well, we gotta compare, you know, these aren't on the chart, but we kind of think of the chart method too. Which one's a better oxidizer, oxygen or carbon dioxide? Oxygen's better. What's a better reducer, methane or water? And when we think about a reducer, we're thinking about burning it or oxidizing it. And so what's easier to burn, methane or water? Methane, yeah, methane's a lot easier to burn, therefore it's stronger. This is weaker. This is weaker. And so sometimes, you know, the stuff that, there's stuff that doesn't appear on the chart, but we still use a similar method as the chart method to figure out. Are we going to figure this one out using the single replacement? No, and the chart method is like this here. When we analyze this, this is a solid lattice, so it's not broken apart, but in that solid lattice we have an oxide. And so when we think about water, hey, water, can it be a good reducing agent too? Oxygen's -2. So isn't that electron rich? I know methane is electron rich because carbon's at -4, so this burns easily. Can't they burn water because oxygen's at -2? Does water burn because it's got oxygen, and oxygen's -2, and therefore it's electron rich? Or is it just happy as is? Is water stable or is it flammable? It's stable. And so that tells me something. That tells me that oxygen with 2 electrons is stable. What's easier to burn, you think? You think aluminum, metal, or oxide? What's easier to burn, aluminum, metal, or water? Well, once I saw aluminum car burn, aluminum fiberglass car. The car caught on fire at the gas station. It was a Lotus, and it was a molten pool of metal, aluminum metal. It was pretty interesting, but
So I'm not sure, I just wanted to confirm, how did you tell that it was like a redox equation? Versus like another driving force, I'm not quite clear on how you figure out like the driving force.
how did I tell it's a redox reaction?
And then how do you like determine which is, do you look at the chart for the oxidizing agent and then?
Yeah, I just get familiar with oxidizing agents and reducing agents. Just get familiar with that chart. So, for example, I get familiar with oxygen. You know, what's a happy charge? What's an unhappy charge with oxygen? And the same thing. -2 is a happy charge for oxygen. Oxygen likes to be -2. It's stable. How about fluorine? What's a happy charge for fluorine? -1. Is fluoride very flammable? Is it easy to oxidize fluoride? Hey, we want to burn the stuff. Let's say you ran out of wood, but you have a tube of toothpaste and it has a little bit of fluoride in there. Will the fluoride burn? You expect it? Not easily. It'd be harder to burn fluoride than it would be to burn water. Is water something easy to combust? No. What are the easiest things to oxidize? Metals. Have you ever heard of the lithium battery fire? Why? Are metals flammable?
Yeah, metals are flammable. Metals are flammable. Lithium plant burnt down. Not in this country, but in another country. Mitigating fire and explosion hazards of powdered metals. Not only will they burn, they'll explode. Have you heard of metal explosions? You know, does grain burn? Grain, like flour. Does flour burn? Yeah. Will flour explode? Flour will explode. We don't see it that much because we don't live near grain silos. But if you live near a grain silo, this is a big deal. If you live near a bakery, you know how many bakeries have exploded? A lot. You know why they explode? Let's see a bakery explosion. Bakery explosion. 2 escape injury.
Quite a morning here in Belmont. Take a look behind me. Firefighters are still here, investigators, as well as the building inspector. This is Owen's Bakery. It's been around for 100 years. Luckily, this morning, the explosion did not injure anyone. Take a look at the video. The front of the building doesn't appear to have much damage, but in the back, you can see what that explosion did to the rear wall and the ceiling. It's believed to have been a gas explosion from the oven in the kitchen.
Okay, sorry, that's not the right bakery explosion. The bakery explosion is is this. I should have looked before. It has to do with the flour. If you get very fine powdered flour and it goes up into the ceiling fixtures, lights, and if there's an arc, then you have potential for explosion. And so this is so what you have is you have the grain. The grain is finely divided. It makes an aerosol. And that aerosol is highly flammable. You get the right mixture of air and grain in there. And you could have grain silo explosion. The grain silo explosion is what happened to bakeries. These bakeries that have maybe this one's better. I hope like I was alright. That was hard to see, but alright, we'll watch it again. You see, you're getting just the right mixture. Grain's electron rich, you know, carbon, the reducer, and oxygen. This grain silo. So what we do is we get familiar with the chart. We get familiar with the chart because of oxidizers and reducers. And so here, aluminum versus oxide. Well, aluminum is a powerful reducer. Aluminum is a metal. Actually, I forgot to show you the metal fire.
Like a podium title is placed in the top of the funnel mounted inside a large can. A lighted candle is also placed in the can.
You got to get the right mixture. So they put a powdered metal or any powdered reducing agent.
Pressed into place. Air forced into the funnel causes the color to disperse within the can and to be ignited.
So any reducer will do that. Uh-huh.
So are reducing agents electron rich and oxidizing electron poor?
Yeah, right. And so here, we would just analyze this, even though there's no water around, we'd analyze it the same way. Aluminum is electron rich. All metals are electron rich, including the best reducer. What's the most electron rich species on the redox chart? Lithium metal. You better watch out, because if you're going to build a fire, you don't want to use lithium metal. That stuff's going to burn easily. Easily. And then, okay, we have oxide and we have iron 3. Iron 3 is a electron rich or electron poor? What do you think? Electron poor. So this will be our oxidizer. Our oxidizer will be iron 3. Our reducer will be aluminum. This is a very important reaction because this is used in shipbuilding. Have you ever heard of the thermite reaction? Thermite reaction? Actually, we won't watch the whole thing. We'll just watch thermite versus car. Are you ready to see thermite versus car?
It's a powdered mixture of iron oxide and aluminium, which when ignited burns at 2,500 degrees Celsius, which is very, very hot. This is liquid nitrogen. It's specially stored at minus 198 degrees Celsius. That's 163 degrees colder than the North Pole in winter. But is it cold enough to neutralize the intense heat of thermite? Packed into the slow release mechanism of a garden flower pot, the thermite is ready for action. Just like the touch paper, stand well back. The fuse triggers the irreversible thermite reaction. As scorching hot meets freezing cold, a fierce battle rages. The smoke clears, and incredibly, nothing remains. As the thermite burns at 2,500 degrees, it releases a raging torrent of molten iron, which rains down upon the liquid nitrogen, boiling the glacial mixture away in a plume of vapor and melting the cylinder, leaving just a puddle of white hot iron. A clear victory for thermite. So there you go, Dan. Adding something cold to thermite doesn't cancel it out. It just makes it angry. Thermite. You won't like it. This is a car. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of the car. It's basically a huge lump of metal, and well, it's very hard to melt. Lucky then, the brainiacs have plenty of thermite, specially packed into the slow release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine. Now that the engine is melted clean through, it seems only fitting to have a go at the petrol tank. Packed into the slow-release mechanism of a garden flower pot, the thermite is ready for action. Popped under the roof, directly above the fuel tank, top up, and just 4 feet of barreling car stands between the thermite and 8 gallons of petrol. very purple but stand well back.
See the flower pot?
The irreversible thermite reaction begins. Thermite produces a stream of molten iron which melts through the car in seconds. Its 2,500 degree heat igniting the expanding petrol in a devastating fire, leaving behind a car that won't be going very far anytime soon. So there you go.
So what you do is just learn about oxidizers and reducers, and we can place it. For rust is considered electron poor or electron rich. Rust, well, you might say it's electron rich because of oxide, or you might say it's electron poor because of iron 3. Well, which one is it? It's electron poor because oxide is happy at -2. We see oxides as happy at -2 in lots of things. Rust, water, etc. And so these are little reference points you memorize. And then aluminum is a pretty active metal. It's not the most active. If they made that out of lithium and rust, they would have been a heck of a lot more careful, than making it out of aluminum and rust. This would be thermite. And so it doesn't matter if there's water around or no water around, we still use it as is. If there's water around, we consider water too, but water is very unreactive. Water is stable, and it's only in the usual cases that water reacts. You gotta worry about water reacting when you're using very powerful oxidizers or very powerful reducers. Otherwise, water is happy as is. And so this question was, they gave you too many clues. Here, I wouldn't have given you this many clues. The question about lithium and water, they're telling you it reacts. I wouldn't have told you it reacts, I would have just expected you to figure it out. What happens when lithium is added to water? I know something's going to happen. Lithium is the most powerful reducer on the chart. Something's got to happen. Okay, other questions?
From the sample exam, it was question number 30.
This one? Unfortunately, I screwed up the numbering on this.
The other 30. If you want to do both.
This 30?
Just do the whole thing.
Do you need this 30 done or what?
Yeah.
So what's the first step we do? Yeah, so how many grams of oxygen?
94.06.
How many grams of hydrogen?
Yeah, 5.14.
And then that's the mass ratio, then we're gonna get the what ratio?
Mole ratio.
And so, these numbers I have memorized. A mole of oxygen weighs 16.00 grams. So how many moles is that gonna be there? 94.06. Divided by 16. 5.87. About 4 sig big, so 5.878. I'll carry one extra. 87, 87. And for hydrogen, it's usually 101. A mole of hydrogen is 101, but in this case, I want to use one more, so I'm going to call it 108 grams. That'll give me 4 sig figs, but I only have 3 sig figs here, so. 5.94 divided by 108. 5.89. And then we get the mole ratio. I do it a little bit different. Did you notice what I did differently than the book? One thing I did differently than the book is this. I went ahead and got the mole ratio here, so it came out to H 5.8920, O 5.8787. And then the way I did this is I'll pick the smaller. Which of these two is smaller? This one. So let's go ahead and divide it 5.8787, 5.8787. And so 5.892 divided by 5.8787 gives me 1.002. So it's going to be H 1.0024, O 1.000. And then we simplify this. This is going to be HO. This is what we call the empirical formula. How much would an empirical formula unit weigh? How much does this weigh? 17U. So this is going to be about 17U. How much does a molecule of this weigh? 34U. So one molecule of this is double the mass of this. Double the mass of this, that means the molecular unit is going to be twice as big as the empirical unit, which means the molecular formula is going to be H2O2. H2O2 is called hydrogen peroxide. So that's number 30.
Can you do the second
The second 30s is dimensional amount. How many molecules of H2O16H2 are there? Given some information. So in one drop we have 0.05 milliliters of water. So in one drop of water, how many molecules? Yeah. What else are we given in this problem? We're given the mole percent abundance. We're given the mass. So I need to get rid of milliliters or milliliters of water. What can I get rid of? Yeah, so I can get rid of milliliters of water. And so we know in 1 milliliter of water weighs how many grams? 0. So that gives rid of milliliters. It gives me grams of water. Then I need to get rid of grams or grams of water. Is there something that does it? Grams to moles does it. There's 18.02 grams of water per mole of water. I'd have to calculate the molar mass. 2 hydrogens, each at 101 gives us 202 plus 16. And the oxygen gives us 1802.
I have a question. Since we're getting a specific isotope, why wouldn't we use the mass of that specific isotope?
Because you're not given 0.05 milliliters of that specific isotope. We're given 0.05 milliliters of water. If we're given 0.05 milliliters of this specific isotope, then we could use that, except we don't know what the density of. Yeah, and so we have to be given the density in order to get the grams. This says this information is to throw you off. You aren't going to do anything with this information here. You could, I mean, I could ask you how many grams there was. If I ask you how many grams there was, then we'd need it. Okay, now we have moles of water. And we have a mole percent here. What does this mole percent say? Yeah, how much of that specific water molecule is in water? So we're gonna have 0.0132 moles of what? For every 100 moles of H2O. And so the moles of H2O cancel, grams of H2O. That leaves us with moles of that specific water molecule. And then I can get rid of moles. I can just go from moles to number of molecules. Yeah. 6.022 times 10 to the 23rd molecules per mole of molecules. Water molecules. So let's go ahead and calculate this. So it's going to be 0.05 divided by 1802 times 0.0132 divided by 100 times, I would rather 6.022 times 10 to the 23rd. 2.2 times 10 to the 17 H2O16 H2 molecules. And you have a huge number of these in one drop. In one drop, if you just drank one drop of water, how many of these molecules did you just consume? 10 to the 17. It's huge. But it's small. This is a tiny number compared to the total number of water molecules in one drop. The total number of water molecules in one drop is enormous. This is just a small fraction of this. Okay, other questions? Uh-huh.
Is the oxidation state the same as the charge of the atom?
Is the oxidation state the same as the charge on an atom? Yes, on an atom. It's not on a polyatomic. So if you have something like ClO4 minus, this charge is not the same as the oxidation state. But if you had Cl, then this charge is the same as the oxidation state. The oxidation state is the charge on an individual atom.
So then for the polyatomic for chlorate, the Cl with oxidation state of Cl would be 7+.
And so the oxidation states here would be +7 for Cl and -2 for oxygen. -2 for oxygen is very happy, as is for oxygen, you know, and therefore it's very stable, and therefore this is what we consider a powerful oxidizer. It really doesn't go both ways. You know. It really just goes one way. And so if it goes just one way, it's like this, CO2. What do you expect the redox properties for this to be? This is going to be an oxidizer. And not a very good oxidizer. Based on experience, is CO2 a good oxidizer? No, because CO2 is used in fire extinguishers. If you use CO2 in fire extinguishers, it's like if there's a fire, would you grab a cylinder of oxygen gas and start spraying oxygen gas at a fire? No. And so this tells you oxygen is a great oxidizer, CO2 is a really bad oxidizer, and it's an even worse reducer. It's a worse reducer because oxygen is happy at -2. Just like water. Is water a good reducer? No, water is happy with oxygen at -2. It's happy with that, doesn't mean you can't burn the stuff. If you have something powerful enough, you probably can. And it's not a very good oxidizer. As well, it's weak both.
But if you have monatomic, then the oxidation state is just the charge. And so aluminum, what's the oxidation state of aluminum 3+? Well, it's 3. What's the oxidation state of this? AlO4. AlO4. Maybe I shouldn't do AlO4. Maybe do something else. Well, we got pretty. So if it's a single atom, then the oxidation state is the same as its charge. If it's multiple atoms, then we have to figure it out by using the techniques we've been using. Okay, other questions?
Number 24 on the practice exam, there was a question about if how we would know if it's a molecular mass or formula mass. Those are all non-metals, so how would we be able to tell?
This one you have to have memorized. What's below carbon in the periodic table? And so we have carbon dioxide. Is carbon dioxide molecules or a lattice type structure? And so I would expect SiO2 to form molecules too, just like carbon. So this is carbon dioxide, this would be silicon dioxide. But silicon dioxide has another name. What is the other name for silicon dioxide? Quartz. And so if you have SiO2, does it form molecules? Is it like dry ice, you know? Dry ice looks a lot like ice, regular ice, you know? So is quartz like ice, or is quartz like something else? Yeah. And so this is all from experience. So we do this. Chlorine, molecules or lattice? So molecular mass. Carbon monoxide, molecules or lattice? Molecules, so molecular mass. Methane, molecules? I don't even know. I don't even have to know what quartz is, because I know these three for sure. So by a process of elimination, there's only one choice. SiO2. It depends on how confident you are in the first three, which you should be very confident in the first three. All three of those are molecules, therefore this one is the only one that we haven't been able, and this one's ambiguous, we don't know, therefore. And so even if you didn't have quartz memorized, you should have been able to figure it out by elimination. Okay. But SiO2 is quartz. And quartz has a very different structure. You know, frozen chlorine is a mush. Frozen carbon monoxide is kind of a mush, and frozen methane is kind of a mush. But quartz is not. You know, look at quartz crystal. Quartz crystal is very strong. Is dry ice very strong? No. Dry ice is easy to break apart. And that has to do because of the structure. These are two types of quartz. I don't know if you ever use those halogen lamps? Anybody have a halogen lamp? Probably have I don't really have halogen lamps anymore. They used to have halogen lamps. They're banned in a lot of countries now. Big fire hazard, they get so hot. But halogen light bulb you don't want to touch with your fingers. Have you ever heard that?
Do not touch halogen light bulbs with your fingers. You know why? Halogen light bulbs are made out of quartz glass like this. If you touch them, you leave ions like sodium on the surface. Those ions get into the structure. What happens is it forces it to crystallize in the form of sodium silicate glass. The sodium silicate glass is very brittle and can crack easily. So to keep it clean, SiO2, which has a very, very high softening point, or kind of melting point, you need to keep ions away from it. Okay, what else? So here we want to use formula mass, not molecular mass. Because how big is a molecule of quartz? Well, it depends, you know. How big of a crystal you're going to make. Okay, do you want to take a break now? Let's take a break now and then we'll